test today or something?
Yeah.
Analog and power.
Huh?
Analog and power have tests. today.
And signals and
How
systems.
many ever tested it, I'm curious?
There were 3 10.
They're
Or have had one? Wow, okay, well, it's gonna be a fun day. That's all right. Anyway, go ahead, if you have any questions before, I've got things I want to cover, no? You, yes?
You work 4.54.
Yeah.
It's consider a long pair of straight parallel wires, each of radius A.
Okay, so I gotta give a radius. Yeah. These have radius A, go ahead.
And their centers are separated by distance D.
Uh-huh.
Assuming that D is much greater than A, find the inductance per unit length of this pair of wires.
All right, this is sort of a classic problem. There are a lot of problems that are similar to this. So if you're going to solve for inductance, it's sort of like solving for capacitance or resistance. The steps are you assume something. In this case, we assume I. You start there. So once you assume I, remember they want inductance per meter. They didn't say if it's differential or if it's in, it has to be differential in this case, but I'll just show you what I mean by that. There's going to be current I going this way and current I going this way. So it's like a transmission line or an extension cord. Think of it like that. You all with me on this? No, these are wires, right? Now I know if I take a look at this and I want inductance, I have to find an area that flux is going to penetrate, right? Think back for a moment when we talk about the coaxial cable like this, right? We looked at an area that was between the inner radius A and outer radius B of length 1 meter. Do you remember that? Everybody? Same deal here, only now, here's the area. It'll be per meter in this case too. This will be just L here is 1 meter, or the length is 1 meter long. So we want to find the total amount of flux that penetrates there. You all with me? Now this is self-inductance. I want to make sure you hear me on this one. If you think about this, I've got a current going up, right? Take your right hand, put your thumb in the direction of that current. It causes an H field this way and a B field that way, right? Once we integrate, we're going to have to take that into account. And when you come over here, because it's in the differential mode, current down there, that flux will be additive to the prior one. Do you all see that? The B fields will add. Now the neat thing about this is, once we get I can say that the H field from one of the wires, I'll call this 1, or I'll call this 1, this 2, circuit 2. The H field, assuming current 1, the H field here would be I1 over 2 pi. And now I need to add some sort of a coordinate system here. This is a really good problem, by the way. I'm saying that for a reason, because you got a quiz coming up on Friday, right? So when I say it's a really good problem, it means you need to know how to do it well, or any permutation thereof. Are you all with me on this? So I'm just going to put my coordinate axis here as the z-axis, right there. And now I'll use this radial distance measured from here as rho. You all follow me on this? And that means if I come out any distance rho away, I know that the H field here would be given by this equation. I know you've had tests. You all agree with that? It's just a straightforward, like infinite wire equation, right? Now, next, if I want the B field, the only thing, and I gotta make I gotta say one other thing too. I'm assuming that the separation distance D is much, much greater than A. So when I talk about the flux, I'm talking about the flux that's actually in the region. I don't even have to go into the wire typically. We'll get there. We can add that, but it's going to be a minor amount of change. So the B field would be what? This is caused by just I1. It would be equal to what? Just mu, right? Times the H field. Or it's simply equal to mu I1 over 2 pi rho A phi. Agreed? And the B field would be into the plane of that board. Do you all agree with that? Now, next after that, that's the B field from just this current over there. The B field, call it B field caused by current 1. B field caused by current 2 would be mu I2, or really I1, they're the same in magnitude, but then it would be 2 pi, but it wouldn't be rho, would it? I want you to think about this. Now, this center is separated from that center by distance d, right? Y'all with me? I want you to make sure you see this. Now, if we want the B field caused by that current, we know it's going to be I over 2 pi, but the rho is not this rho, it's what? It's d minus that rho. Do y'all see that, class? So this distance right here is d minus rho. Now the total B field is the addition of these two. Do y'all agree with that? So now I could say that the total B field, or B total, is just equal to mu I1 over 2 pi, and then it's equal to 1 over rho plus 1 over d minus rho, A phi. I'm just making sure you see what I'm doing here. Now I add the two B fields together. That's the B field at any given point in between them, right? And I've added a coordinate system. Now to get the magnetic flux, which I need, this is the magnetic flux that would be linking these two, or the magnetic flux flowing through this surface. I hope you understand. I'm trying to really emphasize the fact that surface is the planar surface that is between these two wires. But I'm going to ignore the actual field here because remember, that current is going to be uniformly distributed over that. I'll get to that in a second. Y'all with me? He makes the assumption that D is much greater than A. What he's really saying probably is to neglect the amount of the field inside the wire themselves. Do y'all follow me? All right, so this is going to be equal to the integral of B dot ds over the surface, which is really a double integral, and it'd be the integral of this B field. And here I'm going to do something, I'll tell you about it in 1 second. So it's going to be mu I1 over 2 pi, and then it's going to be 1 over rho plus 1 over d minus rho, A phi. I know you've had tests, but what would the differential surface here be? If we talked about, I wanted the differential surface ds. When I go that way, it's d what? Class?
Rho.
D rho. When I go that way, it's d?
Z.
Right. And what direction would it be in? A phi. Right. So it would be d rho dz A phi. It's a dot product, and the only reason I did that is for completeness. You can see that the A phi dot A phi is going to dot to 1. Do y'all follow me on that? So I'm going to just get rid of that because it's annoying. Now, when I do this, I have to put the limits on rho. Here's where you got to be careful. Remember, he made the statement that A is much greater, D is much greater than A, right? So your gut says, well, I should integrate from here, but that's not the good, you can't do that because the B field in here is not what we've got there. That B field we're going to ignore because that's something where the total amount of current versus radial distance, that the assumption we made to get that B field is not legit. But if we ignore the amount of B field inside that wire, and that's the real key when he gives us that, we have to integrate from A, this is important, A to what? How far do we go?
D minus A.
To what? D minus 2A, right? You're going to find out it doesn't matter if it's D minus A. At this point, you could just put D here and it's not going to matter. But technically, it should be D minus, actually D minus A, pardon me, D minus A. Because if you think about it, this is only A here, right? And total separation distance is D. And then DZ goes from where to where? Because I want per meter inductance flux.
0 to H.
0 to 1, right? We just let H be 1. I just always tell people, anytime you have a chance to choose any value for an arbitrary constant, choose 1. You'll never be wrong choosing it as 1. So the length, it's per meter inductance, so make it just 1. So from 0 to 1. You know, the nicest thing about that DZ integral, it doesn't do a thing, right? You integrate DZ from 0 to 1, there's nothing but Z there. Z evaluated from 0 to 1 is 1. Do you agree with that? All right, so I don't even bother with that. I just erase it. Now this one is the interesting one I want to make a comment about. And I'm going to just see how many see this. If you think for a second, just think about this. I'm going to just look at this wire creating an H field. If I get a B field from that wire, it's really what? Mu I over 2 pi rho in the A phi direction, right? Now if I integrated that B field over here, I would have a certain value for the magnetic flux. Do you all agree with me? If I come here, I got the current here, I would get the same exact B field if the measurement was from here to here is the distance, right? And logically, the integral of that B field from here over this surface would be identical. Do you all see that? How many see that right there? In other words, what I'm really saying is, this integration right here will give me the exact same value as that integration there. Do you all agree with that, class? How many do? No? You back there, you're looking at me like, I'm not so certain. I'm not a car salesman, I'm telling you the truth, right? I'm trying to make sure you see this. You with me on this, class? It will be, all right? Which, the reason I'm saying that is, just do one of these integrals. Do the first one and double it. Do y'all follow me? So I'm just gonna say now, I'll just say it's equal to 2 times the integral from A to D minus A of mu I over 2 pi rho, and it would be D rho. And when I get that, what do I get? I get I get 2 mu over 2 pi, so I get really mu over pi, right, I. And then the integral of D rho over rho is 1 over rho, natural log, right, natural log of D minus A over A. And if you want to, you could assume that this is basically D, or it could be D over A. So that means, therefore, that the inductance per meter of this one, ignoring the internal fields there, really the self-inductance per meter would be equal to mu over pi, because I should put it here. Inductance is going to be equal to the magnetic flux divided by the current causing it. The current was I. Inductance is never going to be a function of current. Do y'all agree with this? And then over here it's going to be mu I times the natural log of D minus A, or it could be D over A minus 1. But that's going to be the same. Now Whitmer's book may have log of D over A, because if D is much, much, much greater than A, then D over A is much greater than 1. Do y'all follow me on that? What's the answer in the book? I'm curious. Who asked this problem? Do you have an answer for me?
Yeah, the answer was mu over pi times 1/4 plus ln.
Oh, all right, he gave you distance then. He gave us dimensions. Must.
It says each wire can be solved using the energy approach. However, H equals 2.
Wait. For the he wants the internal inductance of the wires 2 added on. We can get that in a second. This is the inductance. Major point, major component, major amount of inductance is this. Does he have anything that looks like this? You see him?
Yes, he does.
Yeah.
That's
All right, he has that. Then he has the internal inductance of the wires. We're going to get internal inductance. We're going to add that on in 1 second, all right? We didn't do that part yet. And that's kind of an interesting part too. All right, so y'all follow me what I've done so far. I haven't included the amount of inductance associated with the internals of the wire. Watch this now. I'm gonna do it right here. That was part of today's lecture material anyway. So today was a test day, huh? All right, now we're gonna find the internal inductance. Make sure you write this down. Of wires. And we're gonna do this like his book said. We're gonna use the energy approach. All right. So first, before I do this, I'm gonna say a wire looks like this. It has a certain radius A, and we're gonna assume a certain current I flows in that wire. You all with me on that part? And we're gonna assume it's uniformly distributed over the cross-section of the wire, right? So the cross-section of the wire is pi A squared, the area, right? If I talked about the area, it would be pi A squared. And that would give me a current density inside that wire, J of I over the area, and call it AZ, which would be I over pi A squared AZ, and I'm gonna call this axis AZ to make, or call this the Z axis, make my life simple. Y'all with me on that? You agree that that would be J? All right. Now, if I have that, the next thing I'm gonna do is find out what the actual value is of H and then B at any radial distance. This is, down here, this Z axis, I'm trying to make this cylindrically symmetric. So if I come out any distance rho away from the center of that wire, there would be an H field here, right? You agree with that? And I'm gonna try to show you what I'm thinking over here. This result is interesting. So, now for that one, I know if I take the integral of H, right here, this is the direction of the H field, I'm out a distance rho away. If I take the integral of H dot dl around a closed loop, that has to be the amount of current penetrating that loop. Do you all agree with me there, class? That's standard Ampere law, right? So that means the current penetrating that loop, well, by the way, what is this going to be if I come out a distance rho? What is the integral of H dot dl around a closed loop, class?
2 pi rho.
It's just the circumference 2 pi rho times the H field, right, at that point? So I can say that H phi times 2 pi rho, that's that integral, without going through it over again, right? We've done that many times. Is equal to the amount of current inside. Now look at this. The amount of current inside would be J, which is there, it's constant, I over pi A squared AZ, and then we need a differential amount of surface tension right here. So ds here would be equal to d rho times rho d phi. So it's the wiper arm this way. I'm sorry, it's the differential length this way and the wiper arm size, which is rho d phi. And it would be in the AZ direction also. Actually, yeah, what I should do is this. I'll put rho d phi AZ. Now when I integrate rho, I'm going to go from 0 to rho, and technically I should prime that value. And then phi goes from 0 to 2 pi. Now just realize the only thing I've done there is integrate the current density over the surface area, but I'm gonna make a comment here that'll help you. You see how that current density right here is a constant? Doesn't vary versus radial distance, right? So when I integrate the current density dot ds, really I'm taking this current density's magnitude and multiplying it by the area of this thing. Do y'all see that, class? Ultimately, you can do that integration right there, but I can say that this integral, we can do it. We integrate, az dot az is 1. And then if we integrate d phi from 0 to 2 pi, it's 2 pi. Then when we integrate rho, d rho, we get rho squared over 2, evaluated from 0 to rho, it's just rho squared over 2 times this, and it comes out to I over pi a squared. Then you're going to get the surface area, which is pi rho squared. I want you to take a look at that. You all agree the surface area would be pi rho squared, right? And the current density is I over pi a squared. Now, just with a little thought, you can see that this is really equal to just I times rho over a squared. And that would be equal to 2 pi rho times h phi, or now I can say that h phi is equal to I, and it would be times rho over 2 pi a squared a phi. I want you to take a look at that, make sure you agree with me. In the back, can you guys see it okay? All right. So this is h phi, right? How do we get b? Actually, let me go ahead. You all agree with that part? All right, so next we're going to be talking about using the energy approach to get inductance, in this case internal inductance. So when you had an electric field, E, the energy density was equal to 1/2, right here, times epsilon times the magnitude of E squared. This is energy density. Call it E density. Right? If you have a magnetic field H, the magnetic energy density is actually 1/2 H dot B. There's a proof, a really neat proof we do in upper level courses showing you how you actually get the energy density of the electric field and the magnetic field. But for now, I'm just gonna, in his book, he just tells you accept it. So it's H dot B, but it's really equal to, since H is equal to, B is equal to mu H, it's equal to 1/2 mu H squared. And this is the actual magnetic field's density, energy density. This is E density of magnetic field. And the units of both of these are going to be joules per meter cubed. We use joules. Do you guys use, for energy, use BTUs? Do you, joules always? All right. Well, how many of that thermodynamics? You use BTUs, don't you? Maybe you don't remember. In steam tables, you do? God help you. I hate that. Excuse me, I hope I don't get sick. But anyway, steam tables and things like this are unit conversion nightmares. That's all. I hate to do that. They should have standardized this a long time ago. That's my 2 cents. All right. So, look, that's electrostatic energy density, that's magnetostatic energy density, right? So here's the deal. If you have any type of a system, an inductor, for instance, with a current I, there's a certain energy, total energy, magnetic energy, equal to 1/2 Li squared. Do you remember that? That's the total energy associated with current flowing in a single inductor. You can pull that energy back out. You can also say that total energy can be found, or the total magnetic energy in any region is simply equal to the magnetic energy density over the volume considered. Now that should make perfect sense. Energy density integrated over volume is the amount of energy in the volume. You all with me on that? So now we do an equation, we equate these things. We're going to say that the total magnetic energy inside the wire over some length, say 1 meter, has to be the 1/2 Li squared of that, L being the inductance per whatever, per meter, internal will be equal to the integral of the energy density over that region. Does this make logical sense then? All right, so now I'm going to have to do that over here. Remember, this is my H field. So I've got that, and I think I can do it right here. This shouldn't be very hard. So I want the energy density, and I'm going to do this. I'm going to say 1/2 L, and this will be internal. I'll put it L sub I. The internal inductance times I squared is going to be equal to the integral. It'll be a triple integral because it's volumetric of the energy density. Energy density is 1/2 mu H squared. You all see that over there? Make sure you know this for Friday. That's the energy density, 1/2 mu H squared. So here, I'll take the 1/2 and mu out in front, and it's H squared. Here's H, right? I got a square. You'll notice I get I squared, rho squared, then I get over 2 pi squared, and then I get a to the 4th, right? Y'all see that? And it's going to be times the differential volume. Well, the differential volume would be equal to d rho times rho d phi times dz, and that's just differential volume in cylindrical coordinates. Do you all agree with that? Please just make sure you see what I'm doing, the reasons for it. Okay. After this, I put in the H field, I did the job, right? This is basically, what this is the volumetric integral of 1/2 mu H squared over the volume. That's all that I've done. Okay, where does rho go from, class? 0 to A, exactly, because it's internal, right? So 0 to A. Where does phi go from, class? 0 to 2 pi. And where does z go from? 0 to 1. And actually, I put that down just so it's in your head that you have to include that. But when we actually do it, does this dz integral do anything? Integrate dz, we get z evaluated from 0 to 1 is 1. So technically, it doesn't do a thing. I like erasing it just to make it a little clearer. Now when you do this part, I want you to just take a look at this. I can do this easier than you, I think. You see how I squared appears on both sides? It better, because the inductance is never a function of I. It's a linear, any kind of linear materials. So I just get rid of that. Now the next thing I see is there's a 1/2 here and a 1/2 here. You all see that? I get rid of that too. Now I've got an equation that is the internal inductance of that wire per meter. Do you see this, class? I'm going to evaluate it in a second. It's not going to be hard either. So now I say that the internal inductance of the wire per meter would be mu, and then I have this business downstairs, so it's 2 pi squared, and this is a to the 4th. Those are all constants. Then I integrate rho squared d rho, which is what? Actually, it's rho cubed, because there's a rho out here too. So I have rho cubed d rho is rho cubed d rho integrated. Rho to the 4th over 4, isn't it, class? Right? From 0 to a would be a to the 4th over 4, right? And then I integrate d phi from 0 to 2 pi, which is 2 pi. And now I take a look at what I have. I can see I have mu. You'll notice the a to the 4ths cancel. One of those 2 pi cancels, and now I get simply mu over, and then it's going to be 8 pi. This is a real important thing to take note of. I'll tell you why in a second. Now remember, That's the internal inductance of a wire. What is there one thing about this that should just jump off the board at you? Internal, does the radius of the wire make any difference? Not one bit. It doesn't matter what the radius of that wire is. The internal inductance, this is something that's internal to the wire, not external, does not change one bit. This is a small number. All right. But it is a number nonetheless. And when you take a look at the total inductance of this, remember we had the 2 wires, right? You have to add 2 times that per meter to the final answer, and we'll check this. So I'm going to erase this over here. This is the energy form. I'll give you some problems with that. Now, back to that problem. Was it 54?
Yes.
All right.
4.54.
4.54. Now, the total inductance, this is going to be total, was equal to that mu over pi times natural log of B minus A over A. This is per meter plus twice that, right? So it's really going to be plus mu over 4 pi. And this is going to be mu 0 if it's a non-magnetic. And that's going to be in henries per meter. And that would include the internal inductance and the inductance caused by the flux that's actually between the wires. Do y'all follow me on this? Is that the answer, by the way, that he gives? You go ahead and write it down, but.
Yes. Yeah.
Yes.
All right, but I have one comment, and this is important. Just for a second, think about the ratio of this to this, or of this to this, better yet. All right, if you get rid of the mu zeros, get rid of the pi's, this is 1/4 this right off the bat. Do you agree with that? Now, the natural log of B minus A over A really is proportionally how much? So the self-inductance, or the external inductance for this wire, it starts out being 4 times the natural log really of D over A. Now, natural logs don't change real fast. But if you think about that for a second, I mean, if it was log base 10, it would be different. Well, when you think about the natural log of 20, 30, 40, 50, you can see that it's easy to have at least 10 times more inductance associated with the external region than the internal. And that's typically true of almost any kind of twin lead conductors. Remember that. So the internal inductance, even though people talk about it a lot, doesn't do a whole lot. Doesn't hold much energy or anything like that. All right, that's a good problem, by the way. You got another one for me? Because we're knocking out what I want to cover.
You can do 5.7.
What is it?
4.57.
And which one is that?
It's the one you said is a good problem. I can pull it up right here.
Oh, okay. Let me do it.
All right. You ready? Oh, I'll wait.
Now, I didn't see any rain in the forecast today, but I think tomorrow or late tonight or tomorrow we might have some. But Huntsville's going to get clobbered around 7 tonight, according to the National Weather Forecast and my brother. Because there's a whole line of strong storms west of us moving this way.
Last problem, why did it switch from mu over 8 pi to mu over 4 pi?
Because there were 2 wires. Remember, you got current in one wire and then current in the other coming back. So you have to account for both. If anybody looks on the weather and sees any kind of forecast for the next day or two that you trust, let me know, because I'm a little suspicious about it. I looked at that line of storms and it's coming, it looks vicious.
It's supposed to get bad now, I think at like 12 and then.
Midnight, you mean?
Yes, sir.
This is the time of year, I'll make one comment. I think about 2011, might have been 10, there were about this time of year, right around the 1st of April to the 15th of April, storms come through here. And I mean, the tornadoes they spun up were unreal. It took my friends' houses down up at Lake Martin down to the actual slab. nothing left. They go back to, nothing. And they were, I think they're, what, F5, F4 tornadoes came through here. They clobbered a lot of areas around here. Now, if anybody here lives in Huntsville, Huntsville is like ground zero for tornadoes. They clobbered my brother's up there. We're talking upstairs. It's that time of year. He has a tornado shelter because they've had some wicked ones come through. Anyway, something for this problem. What is it?
Okay, it reads, find the mutual inductance between an infinitely long wire and a rectangular wire.
Okay, this is exactly what I was going to talk about today. Got infinitely long wire. Usually I put it on the z-axis if I'm allowed to. And then they have a rectangular loop. This is a classic problem. And I'll call the width of the loop, I don't know, I'm just going to use W. I don't care what the book says, it's W. The height of the loop, H. And there's only one term there. So I want to know the inductance of this thing. By the way, when I give this kind of problem on an exam, if you aren't familiar with how to do this, if you're just cramming, you really get confused here. So I want to know the mutual inductance between these two systems. And I've got to add one more dimension, and that will be, I'll call this D. So I've got a single loop, conducting loop, in the plane of the board, width W, height H, and I've got an infinitely long wire, and I want the mutual inductance between them. How would you go about that? You have to assume something. I know you've had tests, right? But just go with me. You have to assume something, right? What do you assume? Current. Probably current here, because I've already labeled I, right? After that, the next thing you have to get is what? The H field, right? You've got to get the H field created by that. So I assumed I. Now I get H, and that's equal to mu I over 2 pi rho A phi. Now I'm showing this being rho. I do it this way because it makes sense. You're used to seeing that for cylindrical symmetry, right? Next, after that, what do I need if I'm after inductance? I need the B field, right? How do I get the B field, guys? Just multiply by mu, right? Multiply mu times H, which I already did here. This is actually, that's H. When I multiply it by mu, it becomes B. I'm sorry about that. You with me on this? Now, after that, what's the next thing I need? Think about what inductance always is. That the mutual flux that penetrates a secondary circuit caused by a primary current, right? You all see that this is the actual area. I need the integral of B dot ds over right there, class. So now I need a magnetic flux penetrating that area, and that would be the integral of B dot ds over that surface. Technically, it's a double integral. It's a B mu I over 2 pi rho A phi dot ds. And I'll ask this, what would the differential surface be there, class?
D rho dz and the A phi.
That's right, d rho dz A phi. So I'm going to multiply this times that differential surface, d rho dz A phi. And now, what about the limits for rho? Take a careful look what I've drawn. Rho goes from where? From D to D plus W, right? So rho goes from D to D plus W. What about Z? Since we take a look. 0 to H. Here H isn't 1 necessarily. That's the integral, and you can see that the magnetic flux therefore is mu I over 2 pi. And then we integrate dz from 0 to h. The A phis dot out to 1. We simply get h, and we integrate 1 over rho d rho, we get natural log here of d plus w over w. And that is the magnetic flux, right? Right.
Is that supposed to be over D?
Oh yeah, I'm so sorry, you're right. My bad. Absolutely right. Y'all agree with me there? Okay, now that's the magnetic flux. What's the last step to get the mutual inductance? divide current out of it, right? So then I just divide this by current. Then I get the mutual inductance, and I like to put an M there for mutual. I think in his book he used his L sub M, but I like M. M is a more classic way of doing it. I think probably when you had gross, he would use M for mutual and L for self. I like it that way. So that gets rid of this I, and you can plainly see that that's the mutual inductance for one turn of wire. But I have a comment, and it's important you see this. What happens to the mutual inductance as D gets large? Well, I get the log of what? 1, don't I? What's the log of 1? Right? 0. What happens to the mutual inductance as D gets small? What's the log? If it gets small, what happens? You got W over something very small, it's going to infinity, right? What's the log of infinity? Infinite, right? Natural log of infinity is still infinite, which means as this thing gets very small, it goes to infinity. Now the thing that I didn't say is there is no such thing as an infinitesimally thin current element. They all have some finite radius to them, right? But the closer you get this to this, the higher the mutual inductance. One last thing, that's for one turn. What happens if I have 2 turns of shellacked wire on top of each other to the mutual? Multiply by the number of turns, right? Technically what I like to do on these things is I'll put in there where that's the number of windings, because most of the time when you're dealing with a single coil of wire like that, you're dealing with more than one winding. I mean a single, you might say a turn of wire. And that's important to realize. Okay, now that's how you get mutual there. That's a good one. Did you have another one?
Oh, we can do another one.
I got the next one for you.
Okay, go ahead.
If we have time with the magnetic circuits, we may do it on Friday. Anybody else here besides me affected by allergens? Every time, it's not the yellow ball, it's everything else that's coming out at the same time. But man, feel it. That's why rain sometimes helps to get rid of some of this. Okay, so here's the problem, and I don't know the number on this one, I want to talk about it. Suppose I got a really big loop of wire of radius, that's single wire, I'll just call it radius A, and it's got a current I flowing in it, like so. And then in the same plane, like the plane of a board, I have a much smaller loop. This is a problem in the book, of radius B. And I want the mutual inductance between the outer large coil and the inner small coil. And here, B is much, much less than A. Now, how would you do that problem? I want you to think about it for a second, because I like this problem too. I want you to think, what does mutual require you to do? You have to assume a current, right? Self-inductance too, you assume a current. And you're looking for what after that? An H and B field, right? Now here's the deal. If you just have a single turn of wire of radius A, then, and say the current's going this way, then the magnetic field here, H, is actually equal to I, A squared, and then if this is height Z, and you wanted the H field at some height Z, it would be over A squared plus Z squared to the 3/2 power, would be in the AZ direction. Now, I'm not expecting you to appreciate everything, but remember doing that problem basically? That's for a single turn of wire right here in the XY plane of radius A, and you wanted the H field in AC. Now here, we want the H field. We'd like to get, if we have a current there, we'd like to get the H field inside that loop, right? Anywhere inside. And we can, just make Z 0. So now I can say if I assume I here, I can get the H field on the Z axis, specifically at Z equals 0, and the phi direction is equal to simply I And look at this, when z is 0, I have a squared over a cubed, don't I? Because I got a squared to the 3/2 is a cubed, so it's I over a right there. And that would be, you can call it the AZ direction, but it doesn't matter. Now, that's right on the axis, right here at the center. Y'all follow me on that? Here's the reason I put this, and we're supposed to pass it. If this is very small, then the amount of change in the H field over the surface of that inner surface B of radius B is insignificant. Y'all follow me on that? He's assuming the H field doesn't change much because that B is so small. So it really doesn't change much. And so what that does is that H field will give us a B field, simply mu I over A, and this is for rho less than B. And then we can find the magnetic flux in that surface, and that's going to be simply the integral of the B field, mu I over A, AZ dot ds, and the ds here is going to be simply rho d phi d rho. Phi would go from 0 to 2 pi, and rho would go from 0 to b. But what you really see here is this is mu I over A, and it's just going to be times the surface area, pi b squared. No, I'm on time, but that would be the actual magnetic flux through there. Y'all with me on this? If we assume the H field's constant, we get the B field by multiplying by mu, and then we integrate it over that surface. Since the H field is assumed constant, the B field, just multiply by the surface area. Y'all with me? What's the last step? If that's the magnetic flux that links them to get the inductance, just get rid of I, divide by I. And that is a problem I gave you, and that would be the inductance between the inner and outer loops, the self-mutual inductance. Got one question for you. Just think. Suppose I put 2 turns here, what happens? Double, 3 turns. Triple, all right? Add another turn out here, 2 turns outside. 2 times the number of turns, you follow me? Because then, just think about this. If one loop created H, 2 loops on top of each other would create 2H. Y'all with me? 3 loops, 3H, and so forth. So number of turns on primary times number of turns on secondary is what you weight the single mutual inductance by to find the total. Y'all with me, class? Just remember that. Some of this stuff is useful to know because this is the principle. A lot of this stuff I'm telling you is used in a lot of measuring type devices that I'll talk more about. So on Friday, we're going to go over magnetic circuits, and you've had that with Dr. How many have had that with Dr. Gross? Not a lot of people. Well, you'll appreciate, I'm going to take this from and draw an analogy to circuit components. It's very easy to see that way, and we'll pick it up on Friday there. The quiz is the last 2 homeworks. It's going to be stuff based on the last 2 homeworks, and I'll give you something today to help you understand this. Okay? You want to see me about the quiz? See me right after